Okay, well, we're going to start. Welcome. Friday, November the 6th. We're basically going over Chapter 7. We had a long video in the last class, which in essence covers all the topics. But we're going to go through each of them one at a time. And we'll go through the learning objectives. So first one, explain why a sample is the only feasible way to learn about a population. Can anybody tell me why a sample is the only feasible way to learn about a population? Anybody? You can use your microphone if you want, or use the chat. No one understands why you want to use a sample? We've talked about it.
It makes perfect sense because you need to get a sample in order to test certain things to find out anything about the population.
Right. The other thing is, what if your population is the population of Canada? You're not going to go survey every single person in Canada.
Exactly, you just need a small group of people.
Well, a representative group. Don't say small. It's got to be a number that represents, depending on what you're doing. You know, if you're sampling women in Canada, you'd like at least a percentage from all the provinces and the territories and different ages. Those are the things you have to think about. Second, we're going to describe methods to select a sample, what ways you select samples, define and construct a sampling distribution of the sample mean. We've sort of done this a little bit, explained the central limit theorem when we were talking about central measures, tendency measures. You know, the mean, the median, and the mode. This is somewhat related. And we're going to use the central limit theorem to find probabilities of selecting possible sample means from a specified population. Okay, so probability sampling. Let me show you the video first. It's a short video.
In this video, we're going to look at simple random sampling. I'm a teacher of school, and I'm curious how many teams the students in our school play on. So there's 525 students. I want to sample, do a simple random sample, 50 kids.
Okay, first question. Is that a good sample size? Anybody? Hey, why not Wellington? And continue. Okay, I'm gonna tell people, and in your research proposal and when we're in class or when you're going to ask questions, I want you to start thinking, if you haven't already, think statistically, which means you want to get as much information as possible from whatever source you're doing. So when you say it is not representative, that doesn't tell me anything. Why is it not representative? Right? So what does that mean, Amir? What does 9.52% mean? It's small. Yes, it's relatively small. So what would be a more representative percentage of the population? Right. Well, 50% if you can get a hold of 50. That's sort of like the upper bounds of a sample. But in this case, we're talking 525 students. Getting 50% is a possibility, but probably getting 20 to 30, that's better. I want you to look at this, and I want you to look at the holes in some of these examples here.
What's the population is the first question. The population is a 525. What procedure could I use to get the sample? Could I grab the first 50 kids in the hallway? No, you can't, because you're not allowing for the students that are in classes still. Go see the first 50 kids on the varsity football team. Well, this would not be random because you're not allowing other athletic teams or students that don't play on teams. Be outside and grab every fifth student that is leaving at 3 students. No, again, it's not random. Random would be perhaps to write all the students on a piece of paper and pick 50 of them out. We'll see those people. What is the sample in our case? The sample in this case is 50 people. Idea of what simple random sampling is. Hope it helps you. As always, a very happy day.
Okay. Let me go back to the slides. Okay, so that's just, an example. At the bottom of the slide, you'll see the different sampling techniques. Simple random sampling, which is what he used in that video example. Stratified random sampling. All this was talked about in the original video that's on today. Systematic random sampling, multi-stage random sampling, and cluster sampling. So, for people, you may have siblings, you may have relatives, you may yourself want to do this one day, maybe not. You're doing your dissertation, your doctorate, and somebody's doing the topic, a study into employee motivation of ABC company and the ways of increasing it. You choose survey primary data collection method to achieve research objectives. And primary data collection is when you yourself collect the data. The data that I gave you from the city of Toronto, that's secondary because you didn't collect it yourself. So probability sampling comprises 4 stages. 1, identifying an appropriate sampling frame based on your research questions and objectives. ABC company has 400 employees, and accordingly your sampling frame would be 400, the entire population. Number 2, determining a suitable sample size. You may decide the sample size of 60 employees should be sufficient for the purposes of your research. However, and I'm emphasizing this because I don't think these examples are great. Sample size of 60, can anybody tell me what that percentage is? 60 out of 400? No? 15%? Okay. That's not very high. He says it should be sufficient. I disagree. If you can get, well, in this case, you have a number 400. Theoretically, you should be able to get all 400. If it's technically impossible, then at least try 20%. You'd have 80 people. So number 3, you choose the most appropriate sampling technique and select the samples. In this case, simple random sampling, the most basic form of probability sampling technique, can be applied through the use of a table of randomly generated numbers. I mentioned that on Tuesday. And here's some websites. Even if you just go to Google and you look up a random number generator, something will pop up. So you have to do is choose a starting point in the table, a row and a column number, and look at the random numbers that appear. In this case, since the data run into 3 digits, the random numbers would need to contain 3 digits as well. So you need to ignore all the random numbers after 400, since your target population has only 400. Also choose a specific number only once, and if a number reoccurs, simply skip it and move to the next number. Number 4, check if the sample is representative of the population. And can someone tell me how you can check to see if it's representative? What would be the reasons why you would check to see if it's representative? What could make that difference? There's 400 total employees at this particular company. Let's say you're going to do 20%, so 80 people. How do you know they're representative? No, that's the results you're going to get, John. How do you know that your sample is representative of the company? Remember, a sample has to represent your total. All right? Anybody know? What do you mean by fair? What does that mean to me? Tell me what you mean. Remember, you have to be more explicit. You have to give me more detail. Okay, what happens if people, if they're divided into different departments? What do you have to do? Right, because you don't know whether they're different groups. In simple random sampling, you're making an assumption that everybody does the same job. That's not going to be true. Well, unless, you know, it's an accounting firm and everybody in the firm are accountants. Okay, you're all part of the same group. But if they're not, you want representation from each of the groups. Okay, that's really the most important aspect of sampling. You want it to represent the whole population. Otherwise, you're not going to get accurate data that covers the population. Okay. So the advantages of probability sampling: the absence of systematic error and sampling bias, higher levels of reliability of research findings, increased accuracy of sampling error estimation, the possibility to make inferences about the population, which is what you want to do when you do an analysis. The disadvantages: there may be higher complexity compared to non-probability sampling. It is more time consuming and usually more expensive. However, with the advent of computing and most people having access to computers, you're going to administer a survey. It's going to be a lot easier for you to get these people to do the survey. All right, any questions about that? Right? So why do you sample the population? Obviously, the whole population is very large. It's going to be time consuming to get hold of them. The cost of studying all the items in a population may be prohibitive. If you are working for a company and your boss says, I want you to go sample these potential clients that we're going to have, okay, it's going to take time. The physical impossibility of checking all items in the population, and the destructive nature of some tests, and the sample results are adequate, okay, when you sample the population. What is a probability sample? A probability sample is a sample selected such that each item or person in the population being studied has a known likelihood of being included in the sample. So if you think about probability, there's always a chance, you know, you could draw one card out of the 52 and it could be anything. The same kind of understanding when you do sampling, that anybody within the population could be chosen as part of the sample because that's what you'd like to have. We talked about that. And okay. So simple random sample and systematic random sampling. A simple random sample selected so that each item or person in the population has the same chance of being included. So I think we went through this example of Nitra Industries. The total population is 845, samples 52. Again, that's a very small percentage of the company. And the way that it was done here, the name of each employee, you don't have to do this. This could have been done on a computer now. The questions about simple random samples. It's pretty straightforward. Okay, systematic random sampling. The items or individuals of the population are arranged in some order. A random starting point is selected, and then every kth member of the population is selected. And we're using the same population here of Nitra Industries and a sample of 52 employees to be selected. And first K is calculated as the population size divided by the sample size. So you'd select every, in this case, 16th employee on the employee list, and a K is not a whole number, then you round down, and then select every 16th name on the list thereafter. So let me show you a quick video on this.
This tutorial covers systematic random samples. There's a couple different ways of taking a random sample. One way is called the simple random sample, which is abbreviated SRS. Another is a systematic random sample. So we're going to concentrate on systematic random samples today. A systematic random sample is defined as a sample where every kth individual is selected. So what I mean by kth is it could be the fifth person, so every fifth person, or every 12th person, or every 100th person. Okay, so for example, suppose you're interested in sampling 20 people, so n equals 20, from a population of 200 standing in line for a movie. A systematic random sample can be taken by selecting every 10th person in line. So if we take every person from a population of 200, we'll end up with a sample of size 20.
Okay, here's my question. Is 20 representative of the population in this case? Population of 200 people standing in line? That's okay, so why is it not representative, Amir, of the population? Can you tell me why? That's small, however, and see, this is the important part about thinking statistically. If these 200 people are in line for the same movie, is 20 representative of that? Anybody? Yes? And why is that? Why is 20 people representative of this population? The factor is the same? Okay. You have to be more explicit. What do you mean by the factor is the same? You can speak if you want, or you can do the chat. Use your microphone if you want. Can you tell me more? What do you mean by the factor is the same? There, the key point is it's the same movie, right? So in this particular case, you've narrowed down exactly what you're measuring. You're going to survey a certain number of people who are all going to see the same movie. So if I take 20 from 200, okay, then the key factor here is it's the same movie. You're going to ask the same questions of these 20 people. And because they're all seeing the same movie, okay, we don't, I mean, it's nice to get a bigger sample, but they're waiting in line and maybe they're going in, whatever. But 20 is sufficient. So does anybody have a question about that? Of why, in this case, 20 is sufficient number for your sample? Does anybody not understand why? Okay, everybody good? All right.
So that would be, so this sample of size 20 would be a systematic random sample. Okay, just to kind of see how that would work, I have a smaller population here. So my population here is of size 18. So there's 18 little guys here. And let's say I'm looking for a sample of size n equals 6. Okay, so what that would mean is I would need to sample every third person. Okay, then each of those 6 people will become my sample. So if I sample every third person, I would sample the third person, the 6th person, the 9th person, 12th person, 15th person, and the 18th person. So each of these 6 people would become my sample of n equals 6. So then those 6 people would be surveyed or studied depending on what type of research I was doing. Now, a common question that comes up is a systematic random sample also a simple random sample? So we go back to this example. Remember, a simple random sample is when every person has an equal chance of being selected, and every group of size n has an equal chance of being selected. So what I would say is for this group, depending where I start, everybody has an equal chance of being selected. But what makes this not a simple random sample is, let's say these first 6 people, if we look at these first 6 people, there's no way using systematic random sampling where these 6 people will make up my sample. Okay, because of the way systematic sampling is done, there's no way that these 6 people can form my sample. So because of that, this is not a simple random sample. So although a systematic random sample is random and generally representative, it's not considered an SRS or a simple random sample. The other thing to note is when you're taking a systematic random sample is that it will not be representative if the population is already in some sort of order. Okay, so people kind of have to be mixed up. If they already are in order, it's probably best then just to do a simple random sample instead of a systematic random sample. But if they are kind of in a mixed order, usually a systematic random sample will give you a representative sample. That's the tutorial on systematic random.
All right, is there any questions about that? It's pretty straightforward. Questions on that? All right. Okay. So I think I did this previously. This is just a table of random numbers. This is how old this is. So you certainly can do this on the computer. You know, you have 500 people, you want to select 50 people, you can just have a random number generator from 1 to 500, and you assign the numbers, you are going to select these people. Okay? All right, a stratified random sample. This is a method of sampling that involves the division of a population into smaller groups known as strata. In stratified random sampling or stratification, that are formed based on the member's shared attributes or characteristics. So, as I previously mentioned, you want to interview people in a company. If the company is all accountants, you cannot have a stratified random sampling because they're all accountants. Now, you may subdivide the accountants into, tax accountants. Anybody give me any other accountants? Auditors, forensic accountants, if you have that. And stratified random sampling is also referred to as proportional random sampling or quota random sampling, if you see those names. So when you run an analysis or research on a group of entities with similar characteristics, a researcher may find that the population size is too large to run a research on. So in order to save time and money, an analyst may take on a more feasible approach by selecting a small group from the population. A small group is used referred as a sample size, which is the subset of the population that is used to represent the population. There are a number of ways a sample may be selected from a population, one of which is the stratified random sampling. Now, can anybody think of what another advantage is of using stratified random sampling? When you do your analysis and you have stratified samples, what is an advantage here of doing this kind of sampling? Can anyone think of this? Everybody understand what stratified random sampling is? Okay. So say we have 4 different characteristics identified within a sample or in a population. What can you find when you find the results, when you run an analysis about those 4 different groups? No one? No one has any idea. Okay. Well, when you run your analysis, because you're separated into groups, you will find the mean, the mode, the variance, the standard deviation of the 4 different groups, and you can run an analysis between the different groups. See the differences. So do you understand that? Does anybody not understand that aspect of when you have stratified random sampling or you're grouping them based on a similar characteristic? Everybody get this? All right, that's great. Okay, so as I said, dividing the entire population into homogeneous groups, which are called strata. Okay, so we looked at this where you know the number of MBA students that got a job within 3 months of graduation. You find that there's almost 200,000 MBA graduates. So the researcher might decide to take a simple random sample of 50,000 and run a survey, or better still, divide the population into strata. Take a random sample from the strata. So to do that, he'd create a population group based on, in this case, gender, age, range, race, country of nationality, and career background. And a random sample from each stratum is taken in a number proportional to the stratum size when compared to the population. And stratified random sampling ensures that each subgroup of a given population is adequately represented within the whole sample population of a research study. Stratification can be proportional or disproportionate. In a proportionate stratified method, the sample size of each stratum is proportionate to the population. For example, If the researcher wanted a sample of 50,000 using age range, the proportion stratified random sample will be obtained using this formula: sample size divided by population size times the stratum size, assuming a population size of 180,000. So if we have this, we have the age group 24 to 28, 29 to 33, 34 to 37. Number of people in each group, 90,000, 60,000, 30,000, a total of 180. The sample size, 20,000, 16,667, 8,333 for a total of 50,000. Does anybody see a problem with this, with the numbers? Is there a problem when you have a different sample size for each of these different groups? Yes, no, maybe? Anyone? Brenda, what do you say? Is there a problem with the sample size in the stratified random sampling? Are you there, Brenda? Hello, people. Is there a problem with the size of the sample here? No one has an answer. Okay. Okay, why? All right. Amir, why do you say maybe? Why is there maybe a problem? You don't know. Okay. All right. Well, here's an important point. Look at the numbers: 25,000, 16,667, 8,333. Those are relatively large numbers. Okay? When you have numbers that size, it really doesn't matter if they're that different. Okay? If you have a number like in the first group, you had 25,000, and in the second group, you had 12, that's a difference. Okay? Since all three of these groups are well over 5,000 or 8,000, okay, they're going to be as close to the population of the particular strata group. Remember, the larger the sample size, the closer it meets the population mean. Okay? So, these are perfectly fine. If you have a terrible range like 25,003, there's going to be a problem. Okay. In a disproportional stratified sample, the size of each stratum is not proportional to its size in a population. The researcher may decide to sample 1/2 of the population within the 34 to 37 and 1/3 of the grads with age ranging from 29 to 33. Okay. So it's important to note that one person cannot fit into multiple strata. That's the most important thing when you are putting people into categories. Okay? There should be no overlap. Does anybody have a question about that? No questions? Okay. All right. So here's an example. Talked about it. Population is divided into subgroups called strata. And a population can be clearly divided in groups based on some characteristics. Suppose you want to study advertising expenditures. We looked at this example last class. For 352 largest companies in the United States to determine whether firms with high returns on equity, make sure that the sample is fair representation of the 352 companies. The companies are grouped on percent return on equity, and a sample proportional to the relative size of the group is randomly selected. Anybody find any problems with this table? fine? Is it good? You go ahead. Okay, why is it good, Saharatha? Tell me why it's good. You said yes, so why do you think that this table is fine to look at or to get the results from? And why is it not a mirror? Yes, there's more sample from 10 to 20%. Don't worry about Siddhartha. That's the whole point of the class, right? Okay. This is if you look at this, this is very dangerous. Okay? Even though, yes, it's only 0.02% of the relativity of the total, that means you're only taking one company that has a profitability of 30% and over on the return on the. Okay, yeah, they meet the minimal criteria. But if you look at the ends, we have one with deficit and one with 30% and over, and 5, 20 to 30%. It's a small number. When you have small numbers, does anybody know what's going to happen when you run an analysis on this? When you run a data analysis, what can happen with a small number? Like in this case, 1, 5, and 1. What can happen to your results? Anyone? You might get the wrong results. And in statistical terms, we refer to that as a false positive. Or you can have a false negative. Usually a false positive, which means you got statistical significance. However, because your sample is only 1 on this side and 1 on this side, that can skew the results. All right? So if you're going to get anything out of the class, when you're talking about sample size, you must always have some, as much as you can. I mean, you want to make it proportional, or you want to, not disproportionate. That's what this is. All right? You want it to be equitable. You want to try to get the same number here. Okay? You have 5 groups, so why wouldn't you have 10 from each group, from each sample? Although there's only 8 here, so, get all 8 of them, get all 5. In some cases in statistics, you can use a minimal number 5, but it's very tricky because you have to be very wary of the results that you get. Okay, just remember that is very important. All right, so cluster sampling. This is also known as one-stage cluster sampling, is a technique in which clusters of participants that represent the population are identified and included in the sample. Cluster sampling involves identification of cluster of participants representing the population and their inclusion in the sample group. This is a popular method in conducting marketing researches. Okay, I gather anybody gone on a, what do they call it? When you go to work for a firm for like 4 months, a work term. Has anybody done that yet? I don't think you do that. You're only in your 3rd semester, right? Okay, so if anybody's going to go to a marketing company, next semester, see if the company's yet. Co-op, right? Sorry, out of my brain. See if you get involved in a marketing research. So the main aim of cluster sampling can be specified as cost reduction and increasing the levels of efficiency of sampling. The specific technique can also be applied in integration with multi-stage sampling. And a major difference between cluster and stratified relates to the fact that in a cluster sampling, a cluster is perceived as a sampling unit, whereas in stratified sampling, only specified elements of strata that are accepted as a sampling unit. So accordingly, in cluster sampling, a complete list of clusters represent the sampling frame. And a few clusters are chosen randomly as the source of primary data. So here you have your population. Here's the division of the clusters, okay? You take your sample group where you have one from each here and one from each here, okay? And you have your clustered group. But of course, they have similar characteristics. Okay, so let me get to the video. Okay.
Hi, and welcome to the video on cluster sampling. This is our third video on sampling methods, where the first one was in SRS, just a little review, and the second was stratified. Okay, so here you get a sampling frame, give everybody a number, and use a table or calculator to pick your sample size. Here you go ahead and separate them into strata, okay, which are homogeneous groups, and then you take an SRS from each strata, and that makes your sample. Cluster sampling is the next one, and it's sort of similar to stratified. Okay, so I'll show you. So we have this population. So we're going to kind of do the same thing, but we're not going to call them strata. Okay, we're going to call them clusters this time. What happens here is I'm going to split these up. Okay, so I'll call this a cluster. And you have to be real careful because you only could use this in one case. Okay, so you have this population. We're going to split these population into clusters. And what I'm going to do is I'm going to just reach up here and take this cluster. Okay, and I'm going to take this cluster. Okay, so you select clusters at random. Select clusters at random, okay, using an SRS. You select the clusters, the groups at random using an SRS. And then we perform a census. If you recall, a census is we go ahead and gather all the data. We form a census on all.
Okay, just want to check is there anybody that does not know what a census is? Everybody knows what a census is? Okay, you're collecting all the pertinent data, the relative data that you're trying to examine, all right?
On all clusters. Okay, so when does this work? When does this work? Now remember, I said anytime you get a sample, so essentially that's your sample. Okay, so let's say there was like 50 here and 50 here, so the sample would be the 100 from both of those clusters. Okay, so when does this work? It only works when all clusters are a good representation of the whole population. Okay, so let me just go show you an example where it wouldn't work. Okay, so you have your high school, and you have your freshmen, sophomore, juniors, and seniors. Okay, so let's say we need, we're going to go ahead and sample here. So I'm going to call this 1, 2, 4. Okay, so I name all this 1 to 4. Okay, so I go ahead and enter my table, and I want to pick 2 of these. I want to pick 2. So let's say I'm saying I want to pick 2 classes. So let's say freshmen get picked and seniors get picked. Okay, so the question is the freshman a good representation of the whole population? Are freshmen representative of the whole population? No. So if 1 gets picked and 4 gets picked, okay, are seniors a good representation of the whole population? No. No. So now I have this. I have all freshmen and I have all seniors.
Okay, I just want to interrupt. Anybody that cannot see why that in this particular example, clusters of freshmen and seniors is not representative of the total population? Anybody that cannot see that? All right, everybody can see that they are not representative because they're representing only one particular group. And therefore, you are not getting a representative sample of the population.
Who's missing out? I don't have any sophomores or juniors, so this is a bad design. I can't do that because my sample is not a representation of the population. Okay, so if you think, okay, you have this population, you have these clusters, whatever the case, if cluster 1 looks like cluster 4, and cluster 4 looks like 2, and 2 looks like 3, and 3 looks like 1, and 2 looks like 4, okay, if 1 looks like 2, who looks like 3, who looks like 4, then I'm allowed to pick, and I can randomly choose 1 and 3, and 1 and 3 are my sample. Okay, 1 and 3 are my sample. Okay, and you take everybody from 1 and 3. Okay, so basically that's cluster sampling. I will give a quick example that the book uses, and they say they want to get a. So you have a BVD book, okay? BVD, okay, and there's a lot of pages. There's a lot of pages. So an SRS would be go ahead and randomly pick page numbers, and then you want to analyze how many sentences are in each. How many sentences are in? Let me say how many words per sentence. Words per sentence on each page. Okay, so you have this big book. Okay, so do you believe that page 1 is a good representation of the whole book? Page 2, a good representation. 3, all the way to the last page. Last page. If each page is a good representation of the whole book, okay, meaning that you don't think the book's getting harder as it goes, or it doesn't start easier. If you think page 1 is about the same as the last page, then each page is a cluster. Page is a cluster. So you could randomly pick, let's say 10 pages and check. Okay, you would check each page. That would kind of be like cluster sampling. And stratified would be saying, maybe pick, use every page and take an SRS of so many sentences out of pages, but it kind of gets cumbersome after a while there. And you'll see many examples. We'll talk about many examples of these in classes, but just let you know, we're going to split the population into these clusters, and then you're going to go ahead and take randomly select cluster and then take money from those clusters that you randomly chose. Okay, so that's it.
All right. Are there any questions about that, about cluster analysis? Everybody got it? Yes? Okay. All right. All right, so continuing with cluster sampling. Areas or geographical sampling can be specified as the most popular version of cluster sampling. Specifically, a specific area can be divided into clusters and primary data can be collected from each cluster to represent the viewpoint of the whole area. All right, can anybody think of any cluster like that? Or you might use geographical sampling? Would you say that the Swiss Alps is a cluster? All the mountain ranges in the Swiss Alps. Is that a cluster? Why not, John? Your sample is their mountains. So why is that not a cluster? It's not a valley. So tell me why you think it is not a cluster. That it's a mountain range. It's not one mountain. Okay? There's numerous mountains in the Swiss Alps. I'm just taking all the mountains and putting them into one cluster. Okay? And that's called whatever my mountain range is. I can divide up the mountains into different clusters. You see that? Can you see that? Okay. So the pattern of cluster analysis depends on the comparative size of the separate clusters. If there are no major differences between sizes of clusters, then analysis can be facilitated by combining clusters. Alternatively, if there are vast differences in sizes of clusters, probability proportionate to sample size can be applied to conduct the analysis. You're just taking the proportions. So an example, imagine you want to evaluate consumer spending on various modes of transportation in the Greater London area. Since Greater London is a large area, we need to sample from only 6 boroughs out of a total of 32 boroughs it comprises. There are 3 stages for the application of the cluster sampling. Select the cluster grouping as a sampling frame. So an example above, all 32 boroughs of the Greater London represent the sampling frame for the study. Mark each cluster with a unique number. You can easily number each borough from 1 to 32. You choose a sample of clusters, applying probability sampling. Using systematic random sampling or any other probability sampling, you can choose 6 boroughs from the total of 32. Households residing in 6 boroughs will represent the samples for the study. Does everybody see how this sample was created? Anybody not see how the sample was created? All right. Okay. So the advantage of cluster sampling, it is the most time efficient and cost efficient probability design for a large geographical area. This method is easy to use from practicality viewpoint. A larger sample size can be used due to increased level of accessibility of prospective sample group members. The disadvantage, it requires group level information to be known. Okay, that's important. If you don't know it, you can't do it. It commonly has higher sampling error than other sampling techniques, which is what you do not want. We're going to talk about sampling error, but the higher the sampling error, more inevitably you are going to get incorrect results, or you're going to get false positives or false negatives. Cluster sampling may fail to reflect the diversity in a sampling frame. You have to be positive that in your sampling frame, it is capturing whatever characteristics you want to capture. So you have to be careful when you describe the characteristics. Okay. So in this example, suppose you want to determine the views of residents in Oregon about state and federal environmental protection policies. Cluster sampling can be used by subdividing the state into small units. So this is, if you look at the boundaries, this is the boundary of Oregon. And you divide it into small units, either counties or regions. You select at random 4 regions. Then you take samples of the residents in each of the regions and interview them. So note that this is a combination of cluster sampling and simple random sampling. Okay? Any questions about how they did that? So you can see this is sort of a way when people want to do surveys and they want to get information about population living in a certain area compared to population living in a different area, or they're the same area and you want to see if their perspectives are different. All right, so sampling error. Let me show you what the video on sampling error before we talk about it. And remember, if you have any questions, please tell me. I'll stop the video or whatever we're else doing on the PowerPoint.
Taking probability samples of large populations is considered common practice in the social sciences. Although a random selection process is generally the best way of getting a representative sample from a population, it doesn't guarantee a perfect sample. We must acknowledge that even the best random samples will always be a little different from the true population. We call that sampling error. It occurs when we take a random sample rather than observe every subject of a population. Let's pretend that you're...
Okay, so first important aspect. When you do a sample analysis, you will always get error. You look at the size of the error that you got. The smaller it is, the closer your sample is to the actual population. Okay, so it's important to understand what the sampling error is about.
Conducting a telephone survey on how much people spend during their summer vacation. We call 1,000 randomly selected U.S. households, and just by dumb luck, after 100 phone calls, we happen to get a hold of Mark Zuckerberg, founder of Facebook. He agrees to take your survey. Unlikely, but possible. Let's also pretend that after calling 600 people, you also got a hold of Oprah Winfrey. Again, unlikely. The point I'm trying to make is that if just by random chance or luck, we got slightly too many rich people in our sample, or too few wealthy people, our sample will look a little different than the true population.
Okay, can anybody tell me what would happen if you did this particular survey and you got Mark Zuckerberg and Oprah Winfrey? What do you think would happen? We talked about it when we talked about, what central measure is best to use, the mean, the median, or the mode. So in this case, what would actually happen to your mean? Oh, I'm really surprised, everybody. Okay, and what will the result be, Wellington? What's going to happen? How is it going to be different? Remember, this is the point about thinking statistically. What is the average of the population? What is the average going to be? What's going to happen to the average of their income? It will be high. It's going to increase. And you're talking two people, and you're going to interview 1,000 people, and it's not representative. Correct? Because they are skewing the salary, their income, up higher than what it should be if those two people were not in the survey. Right? Does anybody have any questions about that? Okay, it's very important when you look at that. Okay? These are what are referred to as outliers because either they're too small or they're way too high, especially when you're talking about income. So what is the measure that you should use instead of the mean? I know it's 4 chapters ago. Come on, everybody, it's statistics. So what is the other central measure that you can use? The mood, or you mean the mode? It's not the mood or the mode. So what's the last one? What's the last measure of central tendency? Median, right, Siddhartha, right. Okay, because then it's easy because 50% lie above and 50% lie below, right? So these are all the things that you have to think about when you are collecting data or you're coming up with a research project using your own data. You must be very careful about the data that you collect because you can get, as I said, spurious results, false positives or false negatives. Okay.
Difference is called sampling error. When collecting a sample, we can't avoid sampling error. We can estimate the size of sampling error. And there are ways of reducing sampling error. The margin of error that you commonly see with survey results is an estimate of sampling error. Because it is just an estimate, there is a small chance, usually 5% or less, that the margin of error is actually larger than stated in a report. You can reduce sampling error by increasing the sample size. That is, you can select more subjects to observe.
Okay. First part, the way to reduce sampling error, increase the sample size if you can. That's always important. Okay, increase sample size, the more closely it resembles the population.
As your sample size increases, your sampling error decreases. Increasing your sample size also increases cost, both in time and in money. And after about 1,000 cases, you start to get less bang for your buck. As you can see in this chart, after 1,000 cases, even if you more than double your sample size to 2,500 subjects, you only reduce your margin of error by 1%. You can also reduce sampling error with a good sampling design. For example, if your overall population has distinct subpopulations, then sampling each subpopulation independently may reduce sampling error. But these techniques can only reduce sampling error so far. The only way to remove sampling error completely would be to observe every element in a population, which is impractical, if not in some cases impossible. We simply must acknowledge that survey samples are imperfect, but yet a very efficient and accurate way of studying a large, complex population.
Okay. Are there any questions about that, about sampling error? No questions? All right. So here's another example. A population specification error means that XYZ does not understand the specific types of consumers who should be included in the sample. For example, XYZ creates a population of people between the ages of 15 and 25 years old. Any of those consumers do not make the purchasing decision about a video streaming service because they are not working full time. On the other hand, if XYZ put together a sample of working adults who made purchase decisions, the consumers in this group may not watch 10 hours of video programming each week. Selection error also causes distortion in the results of a sample. And a common example is a survey that only relies on a small portion of people who immediately respond. If XYZ makes an effort to follow up with consumers who don't initially respond, the results of the survey may change. And if XYZ excludes consumers who don't respond right away, sample results may not reflect the preference of the entire population. So what is really important is, along with the analysis, along with your sample size, is the design of your survey, of what you're measuring. Okay? So you can see that all these kinds of factors can increase your sampling error. So XYZ also wants to avoid non-sampling errors, and these errors are caused by human error, such as a mistake made in the survey process. If one group of consumers only watches 5 hours of video programming a week and is included in the survey, that decision is a non-sampling error. Asking questions bias is another type of error. Okay, so if you ever encounter or you're going to be creating your own survey, you have to be extremely careful about how the questions are phrased. You want to capture as many people as possible in your survey because you don't want to bias the survey and you don't want to force the survey and make people make decisions that they really don't want to make. Okay, this course doesn't talk about survey design. Maybe it's something they should. I don't know whether it's covered in any of your other courses, but if those people that are in marketing or any of you are taking marketing courses, I'm assuming that they're going to talk about design. If not, you might want to mention it to them. Any questions about sampling error? Everybody good with sampling error? Okay. Okay. Sampling distribution of the sample mean. Xana's hanging over there. Anyways, sampling distribution of the sample mean is a probability distribution consisting of all possible sample means of a given sample size selected from a population. All right, let's see. Let's look at the video first, and then we'll look at the example. Sorry, it's a little slow. Oh boy, okay. This is a rather long video.
Distribution of the sample mean x bar. We're going to let x1 through xn represent n independent observations from a population with mean mu and standard deviation sigma. In simpler terms, we're drawing a random sample of n observations from this distribution. And we're going to let x bar represent the mean of these n observations. X bar is a sample statistic representing the mean of the sample. Before we draw our sample, we can think of x bar as a random variable. The value of x bar will depend on the sample we draw. If we were to repeatedly sample from the population, the value of the sample mean x bar would vary from sample to sample. So the sample mean x bar is a random variable with a probability distribution. We call that probability distribution the sampling distribution of x bar. There are two important characteristics of the sampling distribution of x bar. I'm stating them without proof here, but I do have a video in which I derive these properties. Mu sub x bar is notation for the mean of the sampling distribution of x bar, and that is equal to the mean of the population which we are sampling.
Okay, first important aspect. the mean of the sampling distribution, X bar, the mean of the sampling distribution of the sample mean is equal to the mean of the population from which you're sampling. Okay, so these are equivalent.
In other words, the expectation of our random variable X bar is equal to mu, the mean of the population from which we are sampling.
So in English, your expectation of your sample mean is that it is equivalent to the population mean. All right, everybody get that? Very important.
The standard deviation of the sampling distribution of X bar, which we'll represent by sigma with a subscript of X bar, is equal to the standard deviation of the population from which we are sampling divided by the square root of the sample size. The standard deviation is just the square root of variance. And so the variance of X bar is equal to that quantity squared, or in other words, sigma squared over n. If the population from which we are sampling is normally distributed, then X bar is also normally distributed. So in summary, if we're sampling n observations from a normally distributed population, X bar is distributed normally with a mean, mu, and a variance of sigma squared over n.
Okay, another second point is you always, unless otherwise told, that you assume it's a normal distribution. Okay? So X bar is approximately equal to the n of mu and sigma squared over n, your variance.
Let's see what that looks like. Suppose we're sampling from this distribution, which is a normal distribution with a mean of mu and a standard deviation of sigma. This distribution given in red is the sampling distribution of the sample mean X bar for a sample size of 2. The distribution in green is the sampling distribution of X bar for a sample size of 4, and the distribution in orange is the sampling distribution of X bar for a sample size of 8. In all of these situations, the mean of the sampling distribution is always equal to the mean of the population from which we are sampling, but the standard deviation is smaller. Here, the standard deviation of the population from which we are sampling, represented by the white curve, is sigma. When the sample size is 2, the standard deviation of the sampling distribution of X bar, which we represent by sigma X bar, is equal to sigma over the square root of 2. And when the sample size is 4, the sampling distribution of X bar is a standard deviation of sigma over the square root of 4. And when the sample size is 8, like in the orange curve, the standard deviation of the sampling distribution of X bar is equal to sigma over the square root of 8. So the standard deviation of the sampling distribution of X bar decreases as the sample size increases. It decreases by a factor of the square root of the sample size. So if we wanted to cut the standard deviation of the sampling distribution in half, we would need to quadruple the sample size. The main reason we like large sample sizes in statistics is that for a larger sample size, the distribution of a statistic is going to be more tightly grouped around the parameter it estimates. And so we're going to be able to estimate that parameter with greater precision. In probability calculations, we will standardize in the usual way. If we are sampling a single value from a normally distributed population, then that single value, x, say, has a normal distribution with a mean of mu and a variance of sigma squared. To standardize, we subtract the mean and divide by the standard deviation. So if we let the random variable z equal x minus its mean of mu, and divide by its standard deviation of sigma, then z has the standard normal distribution. For probability calculations involving the mean of n observations, X bar is distributed normally with a mean of mu and a variance of sigma squared over n. So to standardize here, we're going to let the random variable z equal x bar minus its mean, which is simply mu, and divide by the standard deviation of x bar, which is sigma over the square root of n. And if we do that, then the random variable z is going to have the standard normal distribution. Let's look at an example of this type of probability calculation. The amount of protein in a quarter-pound patty, or about 113 grams of lean beef, is approximately normally distributed with a mean of 21.4 grams and a standard deviation of 1.9 grams. This is based on information from the USDA nutrient database. Suppose we want to know the probability a single randomly selected patty has at least 23.0 grams of protein. Here again are the mean and standard deviation for the population. And I've plotted in the distribution of the amount of protein in a single burger here. If we let the random variable x represent the amount of protein in a randomly selected burger, then here we want to know the probability the random variable x takes on a value that's at least 23.0. And that is simply the area to the right of 23.0 under this distribution, this area right here. To find that, we can standardize by subtracting the mean and dividing by the standard deviation. And this is equal to the probability that the random variable z, where z has a standard normal distribution, takes on a value that's bigger than or equal to 23.0 minus the mean of 21.4 divided by the standard deviation of 1.9.
Okay. Does everybody, does anybody not see how he got those numbers? Remember, these numbers are always going to be presented to you. You don't have to guess what they are. And it's just like an algebra equation. You're going to have one unknown and you're going to have all the other variables known. So is there any question? Does everybody get this? It's pretty relatively easy formulas, okay? In this case, you know it's 23, okay, minus the mean, 21.4, divided by 1.9, okay, which is your standard deviation.
That's simply equal to the probability that the random variable z takes on a value that's bigger than or equal to 0.842. And we draw out our standard normal curve, 0 in the middle. Out here somewhere is 0.842. We need this area here. If we go to software or a standard normal table, we can find that the 3 decimal places, this is 0.200. So that's the probability we're looking for. That last question involved the amount of protein in a single patty. Here the question changes a little bit. What is the probability the mean amount of protein in 4 randomly selected patties is at least 23 grams? Here again in white is the distribution of protein in a single patty. In this question, we're interested in the probability based on the mean amount of protein in 4 patties. And I'm going to draw in this curve in green, which is the sampling distribution of the sample mean in this scenario. This sampling distribution is the same mean for the original population of 21.4. But the standard deviation of this sampling distribution in green is sigma of 0.9 over the square root of n, which is the square root of 4. In this question, we need to find the probability that the random variable x bar takes on a value that's bigger than or equal to 23.0. And that is going to be the area to the right of 23.0 under the green curve, under the sampling distribution of x bar. That area right there. And to find that probability, we can again standardize. We have to remember that when we're talking about the mean of n observations, to standardize, we're going to let z equal x bar minus mu over sigma divided by the square root of n. So here, this probability we're interested in, we're going to turn this into the probability that z is bigger than or equal to 23.0 minus 21.4 all over 1.9 divided by the square root of 4. This works out to the probability that z takes on a value that's bigger than or equal to 1.684. And if we go to software or a standard normal table, we can find that that probability, 3 decimal places, is 0.046. Here, the distribution of the sample mean was approximately normal because we were sampling from an approximately normally distributed population. There is a very important concept in statistics that helps us calculate probabilities involving the sample mean when we are sampling from distributions that are not normal. Let's take a quick look at that. The gist of the central limit theorem is that if we are sampling from a distribution that is not normal, the sample mean will still be approximately normal provided we have a large sample size.
Okay, another important concept. As long as your sample size is large, and when I mean by large, over 100, maybe 50, usually in the thousands. Okay, it will still approximate the normal distributed, the normally distributed distribution.
The central limit theorem is an extremely important concept in statistics. I'm just introducing it very briefly here, but I have another video that goes into it in greater detail. Why do we care about the sampling distribution of the sample? We use characteristics of the sampling distribution of X bar to help us answer questions like, how close is X bar likely to be to mu? In the calculation examples in this video, we happen to know the value of mu. That's not usually going to be the case. In practical situations, we don't typically know mu. It is an unknown value that we're to estimate. We're going to use our knowledge of the characteristics of the sampling distribution of X bar to help us state how close X bar is likely to be to this unknown value of mu. This will help us quantify the uncertainty that was present in this type of estimation. The notion of a sampling distribution of a statistic plays a very important role in statistical inference. One small note to finish. In this video, it was assumed that we were sampling from an infinite population, so that we were sampling only a very small fraction of a finite population. This is typically the case in practice. In the event we are sampling a larger fraction from a finite population, the standard deviation of the sampling distribution of the sample mean changes a little bit from what was given here. We need to use something called a finite population correction factor. The details of that are another talk for another day.
Okay, we talked about the correction factor in the last chapter. You don't have to worry about that. Okay, I know it's a lot. So my suggestion is you might want to look at the video again. All right. So sampling distribution of the sample mean in this example. Artis Industries has 7 production employees, considered a population. Again, remember it's very small. The hourly earnings of each employee are given in the table below. What is the population? The questions are, what does the population mean? What is the sampling distribution of the sample mean for samples of size 2? What is the mean of the sampling distribution? And what observations can be made about the population, the sampling distribution? So first one, population mean is $7.71 found by adding all their salaries, dividing by n, you get $7.71. That's relatively easy. It's, figuring out your average. To arrive at the sampling distribution of the sample mean, you need to select all possible samples of 2 without replacement from the population and compute the mean of each sample. So in this case, there are 21 possible samples found by using the formula here. And remember all these formulas you will have. Okay, and is there anybody that is not familiar with this little icon that represents factorial? Anybody not? Everybody know what factorial means? And when you have 5 factorial, it's 1 times 2 times 3 times 4 times 5. Okay. All right. And this is is the table of all the possible samples of 2. Okay? And what is the mean? Okay, so we have 7 plus 750, all these combinations, divide by 21, 771, which is identical to the population mean. Okay? And what can you say? What observations can be made about the population and the sampling distribution? Can anybody tell me? Nobody can see anything here? What can you observe? This is when you're doing your analysis. What observations can be made about the population and the sampling distribution? Are they different? Is one less than the other? Are they the same? No one? Okay, I know it's getting late, but anyways, they're identical, 771 and 771. Okay? Because in this case, we only have a population of 7. So for this particular example, all the combinations were created. And this comes out to exactly the same as this. Okay? So we have the sum equals 771. Here's the distributions. That's the population distribution. This is the distribution of the sample mean. This is all you had to work with there. Okay. This is the sample mean of all the hourly earnings with the combinations and the frequencies, the probabilities here. Okay. So this certainly represents more of a standard normal curve than this, because it doesn't tell you very much. This is all the combos. Any questions about that? No questions? All right, that's great. I hope everybody's getting it. All right. Central limit theorem was briefly talked about in that last video. So what is it? The central limit theorem, or CLT, is a statistical theory that states that given a sufficiently large sample size for a population with a finite level of variance, the mean of all samples from the same population will be approximately equal to the mean of the population. As I've emphasized, that's very important. Furthermore, all of the samples will follow an approximate normal distribution pattern, with all variances being approximately equal to the variance of the population divided by each sample size. According to the central limit theorem, the mean of a sample of data will be closer to the mean of the overall population in question as the sample size increases, that I've mentioned earlier, notwithstanding the actual distribution of the data and whether it is normal or non-normal. As a general rule, sample sizes equal to or greater than 30 are sufficient for the central limit theorem to hold. That's usually what the magic number is if you're going to do a study. You want an N of 30. And this means the distribution sample mean is fairly normally distributed. In finance, the central limit theorem is very useful when examining return for a given stock or index because it simplifies many analysis procedures. An appropriate sample size depends on the data available, but generally speaking, having a sample size of at least 50 observations is sufficient. Due to the relative ease of generating financial data, it is often easy to produce much larger sample sizes. I'm just curious, have you done any of this in any of your other classes? Have you done any examples of looking at financial data and looking at what it means? No? Amir, no? You're the only one? Everybody else? Everybody else still out there? Okay, no. So you have not looked at that. All right, so this is really important. So when you start looking at financial data, you know that it's going to approximate population data. And here they're saying 50 observations is sufficient. Okay. So the central limit theorem is the basis for sampling in statistics. So it holds a foundation for sampling and statistical analysis and finance as well. Investors of all types rely on the central limit theorem to analyze stock returns, construct portfolios, and manage risk. Okay? So now you know the central limit theorem. Now you know you can be a financial advisor. Okay, so let me show you this little video. And this is from that site I mentioned to everybody, Investopedia. If you get a chance, look at it. Okay, why isn't it doing that? Oh, there it is.
Central limit theorem is a fundamental concept in probability theory. Simply put, it states that the average of a random...
Whoop, this video. Oh dear. Okay, can't be played. So I guess my answer is play it at home. It's only about 2 minutes, so I apologize. Something happened with my internet. That's not good. Sorry, everybody. Okay. So an example is, investor is looking to analyze the overall return for a stock index made up of 1,000 stocks. Does anybody not know what a stock index is? Everybody knows what a stock index is. Yes? You don't know. All right. A stock index. All right. A stock index represents more than one stock. It can represent, 5 stocks. It can represent 100 stocks. In this case, the example is 1,000 stocks. That's what an index is. Okay. And people can invest in indexes, not just individual stocks. They're not ETFs, no. But you will learn about that. So when you learn about a stock index, people can invest in it. They can invest in the Dow Jones stock index. They can invest in the Toronto Stock Exchange index. They can invest in the American stock index. It represents a number of stocks. Okay. So the investor is looking to analyze our return for a stock index made up of 1,000 stocks. You can take random samples of stocks from the index to get an estimate for the return of the total index. Samples must be ran, and at least 30 stocks must be evaluated in each sample for the central limit theorem to hold. Random samples ensure a broad range of stocks across industries and sectors and is represented in the sample. Stocks previously selected must also be replaced for selection in other samples to avoid bias. The average returns from these samples approximates the return for the whole index and are approximately normally distributed from what we learned previously. The approximation holds even if the actual returns for the whole index are not normally distributed. That's also extremely important. Okay, so I have another video on the central limit theorem. And hopefully this one will work. Okay.
In this video, I want to talk about what is easily one of the most fundamental, profound concepts in statistics, and maybe in all of mathematics, and that's the central limit theorem. Central limit theorem. What it tells us is we can start off with any distribution distribution that has a well-defined mean and variance, and if it has a well-defined variance, it has a well-defined standard deviation. And it could be a continuous distribution or a discrete one. I'll draw a discrete one just because it's easier to imagine, at least for the purposes of this video. So let's say I have a discrete probability distribution function, and I want to be very careful not to make it look anything close to a normal distribution, because I want to show you the power of the central limit theorem. So let's say I have a distribution. Let's say it can take on values 1 through 6. 1, 2, 3, 4, 5, 6. It's some kind of crazy dice that's very likely to get a 1. Let's say it's impossible. Let me make that a straight line. Your very high likelihood of getting a 1. Let's say it's impossible to get a 2. Let's say it's an okay likelihood of getting a 3 or a 4. Let's say it's impossible to get a 5. And let's say it's very likely to get a 6 like that. So that's my probability distribution function. If I were to draw a mean, this is symmetric, so maybe the mean would be something like that. The mean would be halfway, so that would be my mean right there. The standard deviation, maybe it would look to be that far and that far above and below the mean. But that's my discrete probability distribution function. Now what I'm going to do here, instead of just taking samples of this random variable that's described by this probability distribution function, I'm going to take samples of it. I'm going to average the samples and then look at those samples and see the frequency of the averages that I get. And when I say average, I mean the mean. Let's say, let me define something. Let's say my sample size, I could put any number here, but let's say first off, we try a sample size of n is equal to 4. And what that means is I'm going to take 4 samples from this. So let's say the first time I take 4 samples, so my sample size is 4. Let's say I get a 1, let's say I get another 1, let's say I get a 3, and I get a 6. So that right there is my first sample of sample size 4. And I know the terminology can get confusing because this is a sample that's made up of 4 samples. But when we talk about the sample mean and the sampling distribution of the sample mean, which we're going to talk more and more about over the next few videos, normally the sample refers to a set of samples from your distribution, and the sample size tells you how many you actually took from your distribution. But the terminology can be very confusing because you could easily view one of these as a sample. But we're taking 4 samples from here. We have a sample size of 4. What I'm going to do is I'm going to average them. So let's say the mean, I'll be very careful when I say average, the mean of this first sample of size 4 is what? 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 6 is 11, 11 divided by 4 is what? 2.75. 2.75. That is my first sample mean for my first sample of size 4. Let me do another one. My second sample of size 4, let's say that I get a 3, 4, let's say I get another 3, let's say I get a 1. I just didn't happen to get a 6 that time. And notice, I can't get a 2 or a 5. It's impossible for this distribution. The chance of getting a 2 or 5 is 0, so I can't have any 2s or 5s over here. So in this, for the second sample, sample size 4, my sample mean for my second sample mean is going to be 3 plus 4 is 7. 7 plus 3 is 10. Plus 1 is 11. 11 divided by 4, once again, is 2.75. Let me do one more, because I really want to make it clear what we're doing here. So I do one more. Actually, we're going to do a gazillion more, but let me just do one more in detail. So let's say my third sample of sample size 4, I get, I'm going to literally take 4 samples. So my sample is made up of 4 samples from this original crazy distribution. Let's say I get a 1, a 1, a 6, and a 6. And so my third sample mean is going to be 1 plus 1 is 2, 2 plus 6 is 8, 8 plus 6 is 14, 14 divided by 4, 14 divided by 4 is what? 3.5. 3.5. And as I find each of these sample means, so for each of my samples of sample size 4, I figure out a mean. And as I do each of them, I'm going to plot it on a frequency distribution. This is all going to amaze you in a few seconds. I plot this all on a frequency distribution. So I say, okay, on my first sample mean was 2.75. So I'm plotting the actual frequency of the sample means I get for each sample. So 2.75, I got it one time. So I'll put a little plot there. So that's for that one right there. And I got the next time, I also got a 2.75. That's a 2.75 there. So I got it twice. So I'll plot the frequency right there. And I got a 3.5. So all the possible values, I could have a 3, I could have a 3.25, I could have a 3.5. Then I had the 3.5, so I'll plot it right there. And what I'm going to do is I'm going to keep taking these samples. Maybe I'll take, maybe I'll take 10,000 of them. I'm going to keep taking these samples. So I go all the way to 10,000. I just do a bunch of these. What's going to look like over time is each of these I'm going to make it a dot because I'm going to have to zoom out. So if I look at it like this, over time, still it's all the values that it might be able to take on. 2.75 might be here. So this first dot is going to be, this one right here is going to be right there. That second one is going to be right there. And that one at 3.5 is going to look right there. But I'm going to do it 10,000 times. I'm going to have 10,000 dots. And let's say as I do it, I'm going to just keep plotting them. I'm going to keep plotting the frequencies. I'm just going to keep plotting them over and over and over again. What you're going to see is that I take many, many samples of size 4. I'm going to have something that's going to start kind of approximating a normal distribution. So each of these dots represent an incidence of a sample mean. So I keep adding on this column right here. That means I kept getting the sample mean 2.75. Over time, I'm going to have something that's starting to approximate a normal distribution. And that is the neat thing about the central limit theorem. So the central limit, and this was a case for, so in orange, that's a case for n is equal to 4. This was for sample size of 4. Now, if I did the same thing with a sample size of maybe 20. So in this case, instead of just taking 4 samples from my original crazy distribution, every sample, I take 20 instances of my random variable, and I average those 20, and then I plot the sample mean on here. So in that case, I'm going to have a distribution that looks like this. We'll discuss this in more videos. It turns out if I were to plot the sample, 10,000 of the sample means here, I'm going to have something that, two things. It's going to even more closely approximate a normal distribution, and we're going to see in future videos it's actually going to have a smaller. Let me be clear. It's going to have the same mean. That's the mean. This is going to have the same mean. It's going to have a smaller standard deviation. So I should plot these from the bottom because you kind of stack it. One you get one, then another instance, and another instance. But this is going to more and more approach a normal distribution. So the reality is, this is what's super cool about the central limit theorem. As your sample size becomes larger, or you can even say as it approaches infinity, but you really don't have to get that close to infinity to really get close to a normal distribution. Even if you have a sample size of 10 or 20, you're already getting very close to a normal distribution. In fact, about as good an approximation as we see in our everyday life. What's cool to start with some crazy distribution, right? This has nothing to do with a normal distribution. If we have a sample size, this was n equals 4, but if we have a sample size of n equals 10 or n equals 100, and we were to take 100 of these instead of 4 here, and average them, and then plot that average, the frequency of it. Then we do take 100 again, average them, take the mean, plot that again. And if we were to do that a bunch of times, in fact, if we were to do that an infinite time, we would find that especially if we had an infinite sample size, we would find a perfect normal distribution. That's the crazy thing. And it doesn't apply just to taking the sample mean. Here we took the sample mean every time, but you could have also taken the sample sum. The central limit would still apply. But that's what's so super useful about it. Because in life, there's all sorts of processes out there, proteins bumping into each other, people doing crazy things, humans interacting in weird ways, and you don't know the probability distribution functions for any of those things. What the central limit theorem tells us is that if we add a bunch of those actions together, assuming that they all have the same distribution, or if we were to take the mean of all of those actions together, and if we were to plot the frequency of those means, we do get a normal distribution. And that's frankly why the normal distribution shows up so much in statistics, and why, frankly, it's a very good approximation for the sum or the means of a lot of processes. Normal distribution. What I'm going to show you in the next video is
Okay. So if you got anything out of it, it's important that you know, and I've been emphasizing, if you're going to increase your sample size, the larger it becomes, the more it approximates a normal distribution. Any questions about that? Okay, so I'm going to stop there. Just a couple of things. So I'm going to remind everybody that the Chapter 6 test will be available as of 5 o'clock today. and you'll have until Monday. Is it Monday? Yeah, Friday, Saturday, Sunday, Monday at 5 p.m. to complete the chapter 6. I sent out the chapter 6 homework, and I believe that's it. We will probably finish chapter 7 on Tuesday. There's no rush, but we'll probably finish it. And if anybody wants to, remember I have office hours on Monday. And are there any questions before we stop? No questions? All right, well, everybody have a good weekend, and good luck on your chapter 6 test. Okay, thank you. Everybody be well.